Hi, my name is Sharsot Burkashani and my project is about electricity spot price forecast on Australian national electricity market. The agenda of this project will be problem definition, aims and background of the project, and methodology flowchart, and we will go over the research design and prediction models and the problem definition. Energy market is changing rapidly. The deregulation of power sector with the new rules and competitive market plus the extreme fluctuation in the electricity price makes decision making hard for the decision makers in the electricity market, for traders and business owners. And that's why having access to an accurate short-term electricity price prediction is crucial. It can help with informed decision making, with profit optimizing, and reducing the risk. The project definition and aims. In this research, focus will be on the Australian national electricity market, specifically on Queensland data. And the study will explore the application of three machine learning algorithms. So multivariate linear regression, random forest, and MLP, which is the multi-layer perceptron. The research aims to provide insight into the effectiveness and it will compare the performance of these three algorithms on the Queensland electricity market. There are some limitations with this project, so we are not going over the climate data like temperature, humidity, and the research could benefit from using customers' demand data under different conditions. Justification and originality. So having access to an accurate forecast of electricity price is crucial for energy suppliers, traders, and consumers. It helps them to make informed decisions and reduce risk and optimize their profits. There has been lots of studies over these topics, and they have mainly used CAT-boost, neural networks, bidirectional LSTM, and combination of these methods. And these studies have been done mainly on European electricity markets on an hourly interval. In this study, I have used random forest algorithm, multiple linear regression, and MLP on Australian electricity data, which has been recorded every 30 minutes and mainly on Queensland data. Electricity price forecasting methodology flowchart. So in this slide, we can see all the steps I took on this project, from data collection and pre-processing to feature selection, time series analysis, statistical modeling, machine learning models, and model comparison and evaluation. So for data collection and pre-processing, I collected 2 years of data from NEM, Queensland data, from beginning of 2019 to the end of 2020, and I did the data cleaning and pre-processing, like removing the outliers and removing the missing values. For feature selection, I decided to use the demand and historical price data. And the time series analysis included partial autocorrelation and cross-correlation for price and for price and demand. And the statistical model performed on this data was multiple linear regression, and two machine learning models were performed, random forest and MLP. And for evaluation of the models, I performed mean absolute error, mean squared error, root mean squared error, mean absolute bias error, Nash-Sutcliffe efficiency, and Wilmot index. Research design. I decided to divide my data to 4 groups based on their seasons, and then I performed random forest, multiple linear regression, and multi-layer perceptron on each of these groups. Now, the steps of this project are data collection, data preprocessing, feature selection, algorithm implementation, and model training and evaluation. Model development can be a future work. Analysis method categorization. So, time series analysis method, statistical modeling methods, and machine learning methods are performed on this data. For time series, partial autocorrelation and cross-correlation has been done. Multiple linear regression has been performed as a statistical model. And for the machine learning, random forest and multi-layer perceptron. Prediction models. Three models were used for price prediction: multivariate linear regression, random forest, and multi-layer perceptron. And I decided to use Wilmot index to rank the model's performance based on their accuracy. Separate models were trained for different seasons of the year, and electricity market behavior is different in different seasons of the year, and that's why I decided to divide my data to 4 groups, and prediction accuracy improved with with individual models for each season. Partial autocorrelation and cross-correlation. We have 2 graphs in this slide that shows us the result of our autocorrelation and cross-correlation. These 2 graphs tells us how many points in the past should be used for prediction. So they gives us the number of the lags. So partial autocorrelation is performed on the price, and the cross-correlation is performed on price and demand. So we can see in both graphs that the lags of 1 to 4 are the best one for the price and for the price and demand also. And in the partial autocorrelation, the lag of number 48, which is data from last 24 hours, past 24 hours, has the highest correlation in the autocorrelation. Models inputs and data preparation. For model inputs feature, I utilized price and demand value with lag of 1 to 4. And for the price value, I used lag of 1 to 4 plus lag of 48. So these numbers were picked from the values I observed from the autocorrelation and cross-correlation analysis as shown in previous slide. For data preparation, data was divided into 4 groups based on their seasons due to different market behaviors in different seasons, and data was trained separate models for each season. And I normalized the data before training and testing for improving model performance, and I applied time-based splitting for test and train data sets, and newer 30% of the data was used for testing. For hyperparameter optimization, I employed randomized search CV from a scalar package for optimizing the hyperparameters, and for MLP, optimize hidden layer sizes and alpha using grid search. Here we see the prediction result for winter based on Wilmot accuracy index. So we can see that random forest has the highest Wilmot accuracy index for winter data. And in this slide, we can see 2 graphs. The left one shows the prediction versus actual, and the right one shows the prediction error. For the winter data, for the test data set, the analysis is done by random forest. For spring data, we can see that multivariate linear regression has the higher Wilmot accuracy. And here we can see the graphs for the prediction versus actual, and for the prediction error done by MLR on the test dataset on a spring. Here we see the prediction result for summer Wilmot Accuracy Index has the highest value for the random forest, and the same graphs done by random forest, prediction versus actual, and prediction error graph. And for fall, Wilmot Accuracy Index has the highest value for MLR. And here we can see the graphs for the MLR prediction on fall test dataset. The left one is the prediction versus actual, and the right one is the prediction error graphs. And when the blue spots are the actuals and the orange ones are the prediction. In conclusion, out of our three analytics models, two of them had the better performance. Multivariate linear regression and random forest were the top performing models. MLR was better on spring data, while the random forest was better on winter and fall. So seasonal performances helped us here to understand that winter and fall predictions are highly accurate when the summer predictions had an average accuracy, and spring prediction was notably very poor. In this table, we can see the Wilmot Index for different seasons, for the best performing models on each seasons, for the train and test data. For example, random forest in winter had the Wilmot Index of 0.93 for train and 0.88 for test. MLR in the spring had the Wilmot Index of 0.58 for train and 0.31 for test. Random forest in summer had the Wilmot Index of 0.87 for train and 0.45 for test. And MLR in fall had the Wilmot Index of 0.85 for train and 0.85 on test. So these numbers shows us the challenges and why there are some challenges in summer and spring predictions. For example, for summer, we can guess that the warm weather makes it hard to predict the demand for the electricity usage. And in spring, MLR's performance in training indicates a potential shift in market behaviors between the training and testing period. The absence of overfitting in MLR suggests a genuine change in market dynamics. And here are a list of, and please feel free to reach out for any questions. Thank you.